Hello. Well, hello, everyone. It's a pleasure to be here tonight to talk to you about fusion energy. I'm Dr. Melanie Windridge. I'm a plasma physicist by background and the founder and CEO of Fusion Energy Insights. We help people keep up to date with developments in the growing fusion industry. Tonight, I'm joined by Ed Guys and Anna Hills, engineers at Tokamak Energy, a private fusion company. We're going to take you on a journey through the science and progress of fusion and show you how we're moving towards an era of sustainable, clean power for all. So, where are we going to tonight? We're going to talk about why we need fusion. We're going to talk about the science, how we replicate the stars. We're going to look a bit at the history and the progress and at the growth of the private industry. And then we're going to talk about some important advancing technologies that are bringing us closer to commercial fusion. So let's dive straight in and think about why we need fusion. Well, we have a huge challenge ahead of us. We have under 30 years to transform the world's energy system. Why? Because we have rising global temperatures. Current trajectory says that we will deliver 2.4 degrees of warming when we really should be aiming to stay below 1.5 degrees. We also have increasing energy demands. We're probably going to see about a 50% increase in energy demand by 2050. And then on top of that, we have energy security issues. We need a safe and secure energy supply. So that's the challenge, but what is the solution? Fusion is the transformational solution that the world needs. It produces no greenhouse gases, it has abundant fuels, it can produce abundant energy, and it's a safe, controlled process with no long-lived radioactive waste. But you might be thinking, hold on a second, we already have other clean energy technologies such as renewables, so why do we need something else like fusion? Well, these are a few other reasons why I think we need fusion. The first one is that 100% renewable grids will be uneconomical. That's because of the intermittency of renewables. And so in order to have a reliable grid, you'd need to build so much redundancy into the system that after a particular percentage of renewables in your grid, so around 60 or 70%, the costs start to get really, really high. So for an economical and reliable electricity grid, you really need to have some kind of non-variable, firm electricity generation in your grid, and fusion could do that. We also have to remember that the problem is bigger than electricity. Electricity is only 20% around of the energy market. So there's 80% of the energy market that's much harder to decarbonize. Things like industrial heat, fuels for aviation and shipping, desalination. Things like this are much more difficult to decarbonize, but fusion could help in these areas as well, because fusion produces heat. And so that can be used for electricity, but also for some of these other purposes. There's also, as I mentioned before, the issue of energy security. We do need an energy source that can be used around the world so that energy is available for all, and we have a secure supply. And also, something that I think is potentially very interesting is, could we undo some of the damage that we've caused? If we have an almost limitless clean energy source, we could feasibly use that to scrub CO2 out of the atmosphere and actually undo some of the damage that we're causing. I also see it as fusion being needed to address the fossil fuel gap. Because if you look at projections of energy use in 2050, like this one from the International Energy Agency, you'll see that there's still a big chunk of fossil fuel generation in the energy mix. So that pink arrow there, that represents about 3.5 billion tons of oil equivalent. To put that into perspective, that's like building around 3 gigawatt power station, like a coal-fired power station or a nuclear power station, every week from now until 2050. So that's a huge amount of energy. And so this is a huge challenge, but it's also a huge opportunity. Fusion could address this fossil fuel gap. I also see it like needing to maintain net zero. It's not enough to simply attain net zero. 2050 is not the end of the line. It's really only the beginning. And we need to have an energy source that's going to give us like long-term, clean, sustainable energy. And so it needs to do that with the population's rising and the energy demand's rising. So we're not just solving the problem that we have today, we're solving the problem that we're going to have tomorrow. And so fusion is necessary to maintain net zero into the long term. Now, the challenge of this energy challenge that we have is immense. And so we need a solution with immense potential. And fusion fuel has the highest energy density of any fuel, apart from matter-antimatter annihilation, which is impractical. But what does that mean? Who here can tell me what energy density is? Anybody? Thank you, yes. So I will take that, the very beginning bit that you said about the amount of energy that you can get from a given mass of fuel. So energy density is the energy stored in a fuel in a given volume of fuel. And fusion has the highest energy density of any of the fuels. To demonstrate energy density, I have some balloons here filled with some different gases, similar volumes of different gases with different energy densities. And I am going to set them alight. So I'm going to get my safety specs and I'm going to put my ear defenders on. And I would advise you to also block your ears. So this balloon, right, we ready? 1, 2, 3. Okay, so that wasn't a tremendous bang. Can anyone tell me what they think that gas may have been? Anyone? This one was just air, simply air. But now we're going to bring in a second one. Thank you. Oops, I'm really making a mess of these ear defenders and the microphone. So this one is butane. We're going to see what happens here. Cover your ears. Woo! So that was a little bit more impressive. Can anyone tell me, do you think that had a higher energy density than air or a lower one? Higher, yes, that's right. Okay, the final balloon that we have here, this is a mixture of hydrogen and oxygen. So now this is really time when you want to block your ears. Ready? Thank you very much. So do you think that one had a higher energy density or a lower energy density than the butane? Higher, yeah. I'll remove the specs too. Thank you. So you can see there the difference in energy density in those three gases. And so that gives you an idea of energy density and the different amounts of energy that we can get out of different fuels. And as I said, fusion has the highest energy density of any of the fuels. And so I think it really puts us on the cusp of a new energy revolution. Now, if you think about it, the Industrial Revolution happened when we moved from using animal power to using chemical power. And the Industrial Revolution, of course, you would have learnt about it in history, it was quite a big thing. So we went from being essentially subsistence farming to having the energy for factories and locomotives, and it brought us to the point where we are today. And so that happened when we went from using animal power, which produces joules per gram, to chemical energy, which produces kilojoules per gram. So that's a 1,000-fold increase. And now, if we move to nuclear power or atomic energy, then we get gigajoules per gram. So billions of joules per gram. So that's a million times increase from chemical energy. So the Industrial Revolution happened when we started, when energy density increased by a factor of 1,000, and fusion gives us an increase again by a factor of 1,000,000. Now, Phil LaRochelle, who's an investor at Breakthrough Energy Ventures, who've invested in 3 fusion companies now, he said, we have no idea what's going to be made possible by being able to use fusion power. It's like the discovery of fire. So fusion is energy dense. Just 1 kilogram of fusion fuel produces as much energy as 10 million kilograms of coal. So that's like hundreds of truckloads of coal. So a fusion power station in one day would be able to use about 1 kilogram of fuel, like a big bag of sugar, whereas a coal-fired power station uses hundreds of truckloads of coal. So that gives you an idea of the difference in the amount of energy. And all of this with 0 CO2 emissions. So now you know a bit more about why we want to do fusion. Let's talk a little bit about the science of fusion. So fusion is a nuclear reaction. It happens in the nucleus of atoms. But it's actually the opposite of conventional nuclear power, nuclear fission. Fission is the breaking apart of big, heavy nuclei to make smaller ones, whereas fusion is the joining together of small, light nuclei to make heavier ones. And this is the process that happens in the sun and the stars, and all the atoms in the universe are made through fusion. I think about it a little bit like Lego bricks. You start with the smallest ones like hydrogen, and you build them up to make bigger and bigger particles. Now, on Earth, we would use the fuels deuterium and tritium, which are types of heavy hydrogen. Those are the fuels that we would use in our fusion reaction. And these fuels, deuterium and tritium, they come together, and when they fuse, the protons and neutrons rearrange, and out of that reaction you get helium and a neutron. The helium is the waste product. The neutron carries away most of the energy of the reaction. Now, there actually are other fusion reactions that people are investigating. Some private companies are working towards proton and boron fusion reactions. Others are working on deuterium and helium-3. But deuterium and tritium is the easiest reaction to do, and fusion is already pretty hard. So most companies are working on deuterium and tritium reactions. But now the big question is, how do we recreate the power of the stars on Earth? Well, if you want to make stellar conditions, you need to essentially get your fuel hot enough and dense enough or close enough for long enough for fusion reactions to occur. Those are the 3 ingredients that you need. So this is N, T, tau, E. That's sometimes referred to as the fusion triple product. These are the 3 things that you need for fusion conditions. And within these parameters, though, there is wiggle room. So you could have high density, lower temperature, and a long, long time, like that's what happens in the sun. Or on Earth, when you need to do things at a shorter time scale, you need to get the temperature much, much higher. So in tokamak devices, for example, where we might be trying to do fusion, you're looking for temperatures that are above 100 million degrees, whereas the temperature in the sun is about 15 million degrees. So the fact that there is wiggle room in these parameters has led to lots of different approaches to doing fusion. So these are all some different designs of fusion machines that people have come up with, and there are others. Over time, the most heavily researched of these approaches is the tokamak concept, on the one hand, which is a ring donut vessel with magnets around the outside that make strong magnetic fields that trap the fusion fuel, or inertial confinement fusion or laser fusion. And this is where you have a small pellet of fusion fuel and many laser beams converge on the pellet, and the fuel pellet implodes, and you get to fusion conditions inside that small fuel pellet. But if we're going to be talking about fusion, then we also need to talk about plasma, because plasma is, or the field of plasma physics essentially grew up through fusion research, because the fuel is always going to be in a plasma state. But when I say I'm a plasma physicist, most people look at me blankly, because most people don't know what plasma is. But what about you, ladies and gentlemen? Who here has heard of plasma? Yeah, great, most of you. Can anyone tell me what it is? Fourth state of matter, thank you very much. It's an electrically charged gas, or the fourth state of matter. And you know about the states of matter. You know that we have solids, liquids, gases, and now we have plasma. Plasma is the most extreme state of matter in the universe. It only exists when there's enough energy in the system to strip atoms apart, like this. At such high temperatures, atoms break apart and become a charged gas called plasma.
the fourth state of matter. Charged particles are affected by magnetic fields. They spin around field lines. So we can use magnetic bottles to trap our fusion fuels.
So that's how magnetic confinement does it. Now, plasmas are actually all around us. You're more familiar with plasmas than you think, because the sun is a plasma, lightning is a plasma, flames, neon lights. All of these things are plasmas that you're quite familiar with. And then this is a picture of the Aurora as well, which is a particular favorite of mine, because I wrote a book about the Aurora once, which was lovely. Different viewpoint on plasma entirely. But now I want to talk a little bit more about plasma and the way that we are able to confine plasma. And first of all, to do that, well, this is where we get into some of the demos. First of all, over here, we have an arc lamp, which is going to make a plasma. And I would advise you to not look, if you can see it, if you're on this side or that side, don't look directly at the arc lamp itself. Look at it through the screen or on the screen up there. Yeah, go ahead. I'm going to make a plasma. This equipment is actually similar to what was used by Humphrey Davy in the early 1800s in this very building when they were first demonstrating plasma. And actually, the basis of the arc lamp, or rather the arc lamp, formed the basis for the earliest street lighting before they had incandescent bulbs. There we go. Nice. So what you're seeing there is like a mini bolt of lightning. There's a high voltage across between the electrodes. And as you increase the gap, the voltage is actually ionizing the air in the gap. So it's stripping electrons away from the atoms in the air. And those electrons are carrying the current. So it's like a little mini lightning bolt or flames across there. Thank you, Mike. And now we also have another plasma here in this tube. We need to get going. And ooh, noise. There we go. And what I want to show you here is the basis of magnetic confinement. So how we can use magnets to manipulate plasma. So we should be able to, can we turn the lights down a little bit, please? There we go. So you should be able to see a plasma here in this tube. And Anna has got a big, strong magnet, and she's going to show how the plasma is affected by this magnet. So you can see that as she's moving it close, the plasma inside there is being moved around. So that's because the plasma is formed of charged particles, and charged particles are affected by magnetic fields. And so this is the basis of all magnetic confinement devices. The tokamak is one such device, but there are other magnetic confinement devices. It's basically using the principle that magnetic fields can be used to manipulate plasmas. Thank you. Oops, turn this off. Thank you. Now that's magnetic confinement, but we also have inertial confinement. So that's you either use lasers, or there's a private company called First Light Fusion using shock waves as well to basically compress a pellet of fusion fuel. So here we've got a fire cannon, I believe it's called, and fire piston, sorry. And Mike is going to demonstrate how an increase in pressure can give us the conditions we need to get to ignition. Whoa. Well done, Mike. I'm glad I wasn't doing that demo. But so what was happening in there is the pressure, the increase of the pressure, it's like a big bicycle pump, essentially, was the reduction in the volume of the air in that tube was leading to it heating up so much that it got past the ignition point of the cotton wool that was in the bottom of that. And it's not strictly the same, but essentially in inertial confinement fusion, they're compressing their fuel pellet down until the conditions in the fuel pellet become what you need for fusion. So that's a little bit about the science. Let's talk a little bit about the progress that's been made in recent years. Because fusion has been researched since about the 1950s. And historically, the research has been going on in public labs and universities all over the world. And these are some pictures from just a few of the experiments around the world. And because of the way that the public labs have operated, and particularly the way that things have been funded, the research has led to these sort of two more heavily researched tracks. And so those are the ones I mentioned earlier. The tokamaks and the laser fusion approaches have been the most researched of all fusion approaches so far. And these have culminated in two very big projects. One is called ITER, and one is called NIF. This is a picture of ITER. ITER is under construction. It's a tokamak. It's being built in the south of France, and it's an incredible feat of engineering. It's huge. It's a worldwide collaboration, so countries from all over the world are building bits of this machine and shipping it to the south of France. This is a piece of the inner vacuum vessel of the ITER tokamak. And if you were to stand inside it, just inside that D part, and look up, it would be a little bit like standing in here, actually, or in a cathedral, just like looking up. It's a very, very big machine. And the magnetic coil that would go around that D shape, there will be 18 of these magnetic coils, and each one weighs as much as a fully loaded Boeing 747. So it's huge, it's immense. And as I said, it's a huge feat of engineering. And this is NIF, this is the National Ignition Facility. This is a laser fusion facility in America. You may have heard about it last year in December when there was a big breakthrough that made the news. And what you're seeing here is you're looking through like some of the lasers into the target chamber where they bombard a small, like peppercorn size, or smaller than a peppercorn, a fuel pellet. And so, again, NIF is another incredible feat of engineering, another huge facility. The downside of these huge facilities is that they take a very long time to build, and they're very expensive. And so private companies are looking at ways to do things differently and generally more cheaply as well. But in the public labs, we have had some very good results, but some of these I'm going to mention are only in the last couple of years, so there's been a lot of progress happening in the public labs. This is from the JET tokamak in Oxfordshire. They produced 59 megajoules of energy from fusion, which they sustained for 5 seconds. And so this is a world record in fusion energy produced. And the 5 seconds is actually very important because 5 seconds is a long time for a plasma. So if you can hold a fusion reaction stable for 5 seconds, it gives you confidence that you can do it for 5 minutes and 5 hours and then keep it going for a fusion power plant. And then this was the NIF result from the news last year. They achieved ignition. They produced more energy from fusion than the laser energy used to drive it. And this is a huge milestone. This is essentially proving the science of fusion. It shows that we can do controlled fusion here on Earth. And it means that you can move on to thinking about how you engineer a power plant. So ignition was a really big result for the fusion community. Then also just a few weeks ago, China announced that they'd achieved a 403-second steady-state plasma. That's over 6.5 minutes. And this was it was a high-performance plasma. So this was really important for future power plant scenarios, that you can actually hold a high-performance plasma steady state for a long period of time. So there has been a lot of progress happening in the public labs. But at the same time, we've been seeing tremendous growth in the private fusion industry as well. Fusion is no longer an experimental science. We're seeing people putting things into practice in the private companies and working on designs for fusion power plants. This chart here is a timeline of fusion companies formation. And you can see that there's been a huge increase in the number of fusion private companies. This is from the Fusion Industry Association report, and I think around half of the private fusion companies in existence at the moment were formed in about the last 5 years. There's now probably around 40 private fusion companies in the world researching fusion, and the field has received around $5 billion in private investment. And so this is really pushing things forward in fusion. Who is investing in fusion? Well, there's a mixture of investors from the early stage high net worth individuals to more strategic capital, such as breakthrough energy ventures, Legal and General. We're seeing energy companies like Chevron, Eni, and Shell, and also sovereign wealth funds. And so it's moving much more into the mainstream investor space now. And why now? Why is this happening now, and why is it an exciting time? Well, over the past 10 years or so, various factors have been coming together. The first is mature science. As I said, fusion has been researched for decades now, and so the science has reached a relatively mature stage. Not everything is solved. There's still a lot to be done, but there's a good, solid scientific basis to fusion now. And then on top of that, we have new technologies, enabling technologies. And this is something that's really important, because I think that the fact that the technologies are always changing means that our capabilities are always changing. So just because something is impossible now doesn't mean that it's always going to be impossible. We've had several technologies that have come in just the last few years that are really changing the game for fusion. And I'm going to talk about some of those a little bit later. One of those is high-temperature superconductors for magnets and magnetic confinement. Another is diode pumps for lasers. I'm going to talk about both of these. But also things like high-performance computing is really important. Machine learning and artificial intelligence are really helping the researchers researching fusion. Advanced manufacturing will enable us to bring the costs down when it comes to building power stations. So these new technologies are incredibly important. Also, in recent years, the conversations around climate change and energy security have been changing. And so these are leading the governments to think more seriously about fusion, and it's also leading to more private investment. And that private investment, as I said, is allowing people in the fusion community, in the private companies, to do different things and to do things faster. So all these four factors have been coming together, and they're really driving fusion towards commercialization. So to talk a little bit about progress across the public and the private industries. This is just a clip from the Fusion Energy Insights blog. We talk about some of the significance of the recent news stories. So if you're wondering about what's been happening in fusion and you want to know more about the significance, then you can head over there and have a look. So the kind of stories that we've been covering, things like the public labs breaking the fusion records that I've mentioned, but also private companies are validating their approaches, and governments are taking notice. We're seeing fusion strategies, regulatory frameworks, and more public-private partnerships coming up. So fusion strategies, the UK was probably the first country to have a dedicated fusion strategy. And last year, the Americans announced their bold decadal vision. And the Japanese, just in the last couple of weeks, have also announced their fusion strategy. There's also been regulatory frameworks put into place. The UK, again, was ahead on this, setting out how they were going to regulate fusion energy. The US, just a couple of weeks ago, have said that they are going to also regulate fusion differently from fission because the risks are very different. So around the world, people are starting to think about how they will regulate fusion. And we're seeing more activity in public-private partnerships as well, so how the public sector can work with the private sector. And this is going to be really, really important, because we're getting to the point now where the technology is moving out of the labs and into the private companies. But the public labs have decades of expertise, and they have facilities that are necessary. And so getting access to those facilities from the private companies is an important way of furthering all of their objectives. So we've already got a public-private partnership in the UK called the Fusion Industry Programme. The US have a couple of different public-private partnerships and a new milestone-based public-private partnership which they're working on at the moment. And these are really going to help the private companies to develop their technologies. So we're hoping to see more of those in coming years. And here in the UK actually has its own plan for a fusion power plant, or a fusion pilot plant at least. So this is the STEP machine, which is the spherical tokamak for energy production. And this is a project that's run by the United Kingdom Atomic Energy Authority. And so the UK is the first country to declare its pilot plant. So that's really exciting. So now I want to move on to talk about some of these technologies that are really important for the development of fusion. The first one I want to talk about is high-temperature superconductors for magnets. So this is important for magnetic confinement fusion, and the reason that high-temperature superconductors are so valuable is because with high-temperature superconductors, you can make better magnets. And if you can make better magnets, then you can get better confinement, and you can make better power stations. So to talk about magnets, I would like to welcome Ed Guys and Anna Hills from Tokamak Energy. And I've got a short animation from a video from Tokamak Energy to tell you why the magnets are important.
Creating fusion energy requires strong magnetic fields to confine and control incredibly hot electrically charged hydrogen fuel, which becomes a plasma. Traditional magnet materials like copper have electrical resistance, which creates unwanted overheating. Superconducting materials have zero electrical resistance when cooled to minus 269 degrees Celsius.
Thank you, Melanie. So you've already heard this term, HTS, or high temperature superconductor, used a couple of times throughout the presentation. But what is it, and why is it so important to our magnet technology? Well, to help demonstrate, we're going to start off by looking at a simple copper tube. And Anna has here a very small but very powerful magnet. So we're going to start off by dropping the magnet through the copper tube and take a look at what happens. Now that magnet is in free fall. It's falling quite normally, but it's obviously falling much more slowly than you might expect. If we were to drop it through a plastic tube, oh, yep, try and catch this one, then unsurprisingly, that's going to fall very quickly, okay? So what's happening here? Obviously, there's some amount of interaction between the magnet and the copper tube, but the copper's not magnetic, so what's going on? As I drop this magnet in here, it's obviously moving through the tube, and that moving magnetic field from this magnet actually induces currents in this copper. And the reason it can do that is because the copper is able to conduct electricity. It's an electrical conductor. But this moving magnetic field induces currents in this copper, and those currents have their own magnetic field. And the magnetic field from those currents opposes the magnetic field from this magnet as it falls, effectively pushing back against the force of gravity. Now with metals, as you may be aware, we can vary their electrical resistance, and we can take advantage of this. If I was to make this copper tube warmer, it's going to increase its resistance. At the same time, if I make it colder, I'm going to decrease its electrical resistance, and we can have a look at what effect that might have. So over here, we have a very similar copper tube that's been cooled down in liquid nitrogen. So this is now at 77 Kelvin, or minus 196 degrees C. So Anna, if you can just pull that out for me. There we go. And very carefully, we're now going to repeat the experiment.
Dexterity is not great in these gloves. There we go.
And this time, hopefully it's quite obvious that it's taking far, far longer for the magnets fall through. There we go. Okay, so thank you. So with the reduction in the resistance of the copper, those currents are able to form and flow more easily, and therefore they have a stronger magnetic field opposing the falling magnetic field of the magnet. But what if we could take away the resistance altogether? In most materials, most metals, that doesn't happen. As I could make this copper as cold as I want, it will still have some amount of resistance. But in superconductors, this is what we see happen. So, I've got my beaker over there. So on the table here, I've got a small chip of superconductor. I'm just going to put these glasses on in this pot. And, well, it looks a little bit like this. And I'm just going to add to that some liquid nitrogen. And this will take a second to cool down. So I've mentioned the term HT, or high temperature superconductors. You might be thinking that's a bit strange. I'm still having to cool it down in liquid nitrogen. What's high temperature about that? Well, there also exists some materials called low temperature superconductors, but they require to be cooled down to temperatures as low as 10 or even 5 degrees Kelvin, minus 269 or minus 261 degrees C. With high temperature superconductors, we don't have to cool them down that far, and that gives us big advantages when we're looking to make magnets for fusion technologies, because the efficiency we get at these higher temperatures has big benefits for us. So once this is cooled down, here we go. I'm just going to give it a little bit more. So in this superconductor now, or in this chip in here, it's become superconducting. It's sat on top of a track of magnets. So it's now going to want to repel the magnetic field from these magnets by setting up its own internal currents that oppose that magnetic field perfectly. And what this hopefully means is, when I take my base away, that has not worked. Let's add a bit more. Of course, it goes perfectly every time in practice, and then it does take a little while to cool down because it has to cool all the way through, and it's quite a large piece of material, as you can see there. Right, let's try again. There we go. Okay. So now I've taken away the thing that the little polystyrene cup was sat on, but you can already see it's moving backwards and forwards quite happily. There's no resistance there, there's no friction there, and that's because it's actually levitating above the magnetic track. But it's doing more than levitating, it's actually almost locked in place. Some of the magnetic flux lines for this superconductor are passing through, and this superconductor now wants to stay over the track in the same position. So even if I try and push it to one side, very gently, it's going to basically not move. It's quite difficult to push off. And that also means, on this track, I'm able to push it in one direction, and it's going to carry on, going around the corner, and back again. And as it warms up, at some point, that superconducting property will disappear, and it will just suddenly vanish. It suddenly gains its electrical resistivity back again. So this is very cool for demos like this. But how can we take advantage of this in our magnets? Anna?
So what I have here is effectively two cables. So this one is a fairly standard cable made of copper. There's maybe 1.5 centimeters worth of copper in the middle there. This is a piece of high temperature superconducting tape. And actually, while this tape is about 1/10 of a millimeter thick, the high temperature superconductor within it is only roughly the thickness of a human hair. There's a really, really tiny amount in here. Now, when we cool these both down to liquid nitrogen temperatures, so 70 Kelvin-ish, they'll carry about the same amount of current. You know, you're looking at a couple of 100 amps. Where it gets really cool is if we make it even cooler. And we take this down to 20 Kelvin. So it's another 50 degrees below freezing point of water. And that's the point where this tiny amount of superconductor will carry 5 times the current of this massive amount of copper. And it does that without any resistance, right? So it's not going to electrically heat, which is really, really useful. And that's great. That's one tiny piece of copper, fair amount of current through it. But we can multiply that effect. So I could take loads of these, loads of pieces of high temperature superconductor, stack them up, and make a large cable. Or I can wind it into a coil. So this is one continuous piece of high-temperature superconducting tape. There's a fair amount in here. It's wound quite tightly. And because there's so much in one small area, you get a really, really high current density. So there's a lot of current in one place. And that current is what we use to generate a magnetic field. And actually, the scale's even more. So if you remember the picture of the coils from ITER, it's a similar concept. It's just this on a massive scale, so you get an even more powerful magnetic field. And that's how we confine the plasma.
In our next spherical tokamak, we will use groundbreaking high-temperature superconducting HTS tape. When wound into specialist coils, HTS tape generates much stronger magnetic fields, takes up less space, and requires 5 times less cooling power. An ideal power plant solution to provide fusion energy for all.
Energy is pursuing fusion through the combination of 2 world-leading technologies, the high-temperature superconductors that you've just heard about, and the spherical tokamak shape. So rather than having a ring donut-shaped vessel, you have a more of a chord apple-shaped vessel. So everything is just squashed into the center a little bit more. And this makes more effective use of the magnetic field, which is strongest at the center. And so it makes for a more efficient design of power plant. And so that's what Tokamak Energy is researching, and it's also the design that's going to be used for the STEP power plant as well. It's actually a design that was pioneered here in the UK, the spherical tokamak design. So that's what Tokamak Energy is working on. But now I also want to talk a little bit about laser fusion and the technologies that's improving laser fusion. And this is diode pumps. So to talk about that, I'm going to tell you a little bit about how a laser works. So a laser is... in the very center there, if you look at the picture above, the first picture, you can see that there's a rod in the center, a kind of pink-colored rod. This is a ruby crystal. Some lasers use other types of glass, like doped glass, but this here is a ruby. And so you've got a rod of some kind of lasing material in the middle, and then wrapped around the outside, you've got a light. This is essentially a flash lamp or an incandescent bulb, like a camera flash. And what happens is the flash from the flash lamp, the light from the flash lamp goes into the ruby crystal, and it causes the atoms in there to become excited. And when they're excited, they release light. So they release their own photons of light. And these photons are all the same wavelength. And so you can see then that you've had the flash of light, and then in the third picture, these photons that are generated in the ruby, they bounce back and forth between mirrors that are at either end, and these photons trigger other atoms in the crystal to release more photons. And so it just builds and builds and builds until you've got more and more photons bouncing back and forth between these mirrors, and then eventually the beam emerges through a partially reflective mirror at the end. That's in the fourth picture. So that's how the laser is working. The thing is that in order to trigger those atoms in the ruby to release photons, they only need to be excited by a particular wavelength of light. So it's quite a narrow band, if you like, a narrow region of color of light that's required. But the flash lamp produces white light, so it produces a whole kind of rainbow spectrum of light. And so this is the big difference between flash lamps and diodes, because instead of producing a big rainbow, you could just produce... you'd save energy if you produced less. So here I'm going to show you... I need to switch to the camera. Here I'm going to show you the spectrum of light, or the light that's produced from an incandescent bulb and from a diode. So I have here a diffraction grating, which is going to break the light out into its spectrum of colors. So if I put that in front of the camera here, you can see if I press the incandescent bulb, you can see the little spectra there. You can see it's all big rainbow colors. There's lots of different colors of light coming from that bulb. Whereas if I press the diode, you can see it's just red. that's all that's coming from the diode. So it's a single wavelength of light rather than the rainbow colors that are coming from the incandescent bulb. And so if we can switch back to the presentation, please. So a nice little graph here for you. You can see here that, so we've got the energy of the photons along the bottom, or the wavelength, they're related, the wavelength that's being produced, and the number of photons. So you can see the flash lamp, which is in the orange curve, that's producing a wide range of different photon energies or photon wavelengths, as you saw in the demonstration. It's producing a whole rainbow of colors. But the photon energies that you need to excite the atoms in the ruby crystal is like that pink line there. So you only need a very narrow band to excite the crystals. And the diode pumps produces that blue spike that you can see, so a much more narrow wavelength. And so you're not getting all of that wasted heat, because all of those the wavelengths outside of the pink line are essentially just wasted. So in the lasers that use flash lamps, like the NIF laser is only about 0.6% efficient, whereas a diode laser is more like around 20% efficient. So there's a huge difference in efficiency by using this technology. So some of you may have, if you remember seeing the news in December about the NIF ignition result, you may have seen people saying in the news, like, okay, yeah, so they actually produced around 3 megawatts, megajoules. They produced around 3 megajoules of energy, and they put 2 megajoules of energy into the fusion pellet. So they did produce, they got more out than they put in, which was great. But people were saying, but the fusion, the laser required, the energy required to drive the laser was something like 200 megajoules, so orders of magnitude more. So therefore, we're miles away from a power plant still. And so, yeah, that is true. But the diode pumps are really helping that, because they'll be able to reduce the amount of energy that's required to drive the lasers, so increase those efficiencies. So this is another key technology that is going to help drive us towards fusion commercialization. So fusion is moving into the engineering phase. There are lots of challenges on the way, but we're moving from the scientific research into how you actually engineer a power plant. So there are lots of technologies that still need to be developed. Some key ones are tritium breeding and handling, because tritium is one of the fuels and it doesn't exist naturally, so it will need to be bred in the machine. It's also radioactive, so it requires special handling, so tritium breeding and handling facilities will be required. Material science is also a really big research area, because the fusion environment is really hostile. It has high temperatures, high magnetic fields, high energy neutrons. These neutrons are very damaging to materials, so there'll be new and stronger materials required, and a lot of facilities will be required to test these different technologies as well. We also need to develop supply chains. High temperature superconductors are a good example of a very new material, so supply chains need to be developed. There are other things, specialist components, things like that, but also people and skills are really important as well. We're going to need more people coming into the field. There'll be lots of jobs opening up in fusion as there are more and more companies. So all of these things are challenges as we move into the engineering phase. These are some of the private sector ambitions. There are private companies like Tokamak Energy who are focused on bringing a fusion pilot plant to market in the early 2030s. So this decade is really about proving out the science and the technologies that we need. Some private companies are aiming to demonstrate getting past break-even as well in their devices. And then many of the private companies are aiming to get first electricity generation in the early 2030s, and then they'll be moving on to first-of-a-kind pilot plants in the mid-2030s. So these are ambitious timescales, but we believe it's important to have ambitious goals and to push as hard as we can. So this is a vision for 2050. Net zero emissions, fusion contributing alongside clean fuels, nuclear, solar and wind. There'll also be a whole R&D knowledge economy growing up. There'll be energy security by diversification and lots of high-tech industry jobs. So this is a vision for the future with clean energy. So if you're interested in fusion energy, what can you do? You can tell people about fusion. You can educate young people. They're going to be the ones living with fusion, maybe even working in fusion. You can follow fusion companies on social media to keep up with the progress. You can demand change. We're seeing a lot of governments taking things like fusion a lot more seriously now, but you can add your voice. And you can stay informed. This is where Fusion Energy Insights comes in. We have a free newsletter that you can sign up for. We have blogs where you can look into the significance of the various news stories and get other insights into the commercialization of fusion. So do go and take a look. So just to summarize quickly some of the things we've talked about today, fusion is the energy of the stars, and the world needs fusion as a long-term sustainable energy source. There has been exciting progress from public lab fusion experiments in recent years as they're demonstrating the science. The fusion landscape is transitioning from public lab dominated towards private company dominated with public-private collaboration. New technologies are changing the possibilities and bringing commercial fusion closer. And there are numerous challenges still to tackle, but private companies have comprehensive plans and government support is growing. So it's a really exciting time. And now is actually a crucial time as we move towards the era of commercial fusion. It will require dedication, investment, smart people, and public support. So I hope we have yours. Thank you very much. Thank you.